Thanks for sending the email re-upload. So unfortunately, I couldn't find another time to do analyst, but so Wednesday.
Thank you so much.
Yeah, I'll let you know which room, but I'll just come to that.
Okay, thank you so much. Perfect.
Oh, do you want me to make them up or?
I can. No homework this week, right?
No homework this week. Please, what's it covering? It's like that.
Actually, I don't have credit for
Yeah.
I know.
Yeah. That way, if it picks up noise from someone else, you want to switch. And there's that, the previous recordings, it was like, so like switch to you and so just show blanks.
No.
Okay. Right, so last time we were talking about friction and we got some practice with that on Friday. And so a little bit of circular motion also. Today we'll do a bit more of circular motion, circular dynamics. So I'll start with, ended with this question last time. So, yeah, we'll just discuss this because you did work on it already. So the question, we had a ramp of angle theta and block of mass m resting on it that does not slide, and the question was, what is the magnitude of static friction? So if we yeah, I'll do it on the whiteboard here. So draw the free body diagram. What are the forces acting on the block? There's gravity. What else? Normal force. And I had some friction. Which way would the friction be?
Upward.
Upward, up the slope, yes. And what kind of friction would it be? Static friction, because there's no actual sliding going on. All right, and we're told that it's at rest, it's staying at rest, so we have acceleration equals 0. So then if I add on axes. Let's say I make this one X and this one Y. I know that this angle is theta, which means that this angle is 90 minus theta, which means that this angle is theta again. And so if I write my X and Y Newton's second laws, F at X equals MAX. In the X direction, I'll have force of static friction, and then minus mg what? Sine theta, yeah. Mg sine theta, 2.0. And in the Y direction, similar equation, we have Fn minus mg cosine theta equals 0. And so yeah, so from here we see that, oh, the force of static friction equals mg sine theta. And so the answer is A. And the point to always remember is that static friction is an adjustable force, right? And so we would have force of static friction is less than or equal to μs times Fn. Or if you want force of static friction max is equal to μs times Fn. But nothing here tells us that we're at the max situation, right? So at best, maybe you could say that like, oh, two of these answers are correct, but then they would both have the same value. And so A would definitely be the correct answer. Okay. All right. So yeah, okay, let's do a bit of simplification. Yeah, okay. How about, okay, we'll do one more friction problem before we go on to circular motion. So go ahead and try this problem. Block. So as usual, your first step should be what? Free body diagram. Yeah. So just draw the general situation here. B is on top of it. Yes. All right. Have at it. Give it a shot. Go ahead, go ahead. So draw a free body diagram for each of them individually. And in cases like this where the blocks are moving together, it's also usually helpful to draw one for the two of them together. That means like is not moving. So that is the Einstein. But there's only friction between the six axes. It tells us a frictional state of flows. A and B is on A and then floor on. For A. And technically A on floor. Well, remember, don't, I mean, yes, in this case, but don't assume, always figure it out from the free body diagram. But the normal force like that is also best. Yeah, that makes two force. So, how did we figure out the direction of so just keep so
Well, it could be.
So there should also be a forces of friction.
So, okay, so you need
A is like around 5. No. I won't accept the equations without diagrams. You gotta justify it. Because this is force of friction of A on B, so there must be a force of friction.
And that's don't forget to teach this. The two bosses.
Force of friction of B, is that right? That's understood. Technically, this force of friction is a force of friction that A has used. So it should also be a force of friction. So it must be saved like this or not.
It's the summer.
Well, they are only here, so yes, they will listen. So this is when the overall frequency diagram comes in. So use that for your acceleration, and then you can go back.
Okay, so I did the first round together. And then we went back to making adjustments. And then, right, yeah, that, and so then it's gonna be basically that's the system.
Okay. Well, just the magnitude, which would be the same as the magnitude of B. Okay, so let's see what people think. Show me your votes. All right, got a mix of answers. So I want to emphasize, like, when we do problems here, you want to start getting into it, right? Because if you just like, I'm just going to wait until, like he talks about the problem, sure, that'll work now, but come the exam, right, there's not going to be anyone to wait for. And getting over this hurdle of how do I start a problem? How do I, just even that like mechanical step of, oh, let me draw the free body diagram, let me write the equations, just getting it moving like saves you so much time, right? It like gives you something like, okay, I'm just going to do this automatically, and then when I then have to pause and think about it, I'll have something to work with. I'll have equations to work with. So it's hard. I know it's hard getting over that first hurdle of let me just start, but it is worth it. All right, so let's see what would be the best. All right, I'll put up the screen and do a blackboard. You just jot down the numbers we need. So we have doing A is 13 newtons, way to B is 5 newtons. What else do we know?
It's 0.4.
Yes, it's 0.4. Anything else we need?
External force.
External force, yes. External and 0.5. All right. Hold that on. Okay. So I'll draw the free body diagrams for A. Well, actually, I'll start with B. So for B, what are the forces? Call them out. For gravity, so we have MVG. Normal force, and who's exerting it?
A.
A is exerting it on B. This is on B, remember? Yeah, so normal force of A on B. And yes, there's also friction, right? So we have the force of static friction of A on B. And it is accelerating to the right. Questions about this? Are you comfortable with like the direction of friction, stuff like that? Question, yeah.
Why does it matter that it's force normal A on B versus like just force normal?
In this case, no, it doesn't matter too much, but it's just sort of good to keep track of who's exerting what. Yeah. Also, sort of, it's useful because then when you find the static friction, well, in this case, you don't need the maximum static friction, but in general, if you need to do like a mu times n, right? How do you know which, the multiple normal forces, how do you know which one to use? It's the same one as like between which two surfaces. So that way it's sort of good habit that way. But you're right, it doesn't matter too much in this case. Other questions? Okay. And so then call out the forces. Force of gravity, all right, MAG. Normal force of Ground on A, okay. So I'll put that as floor on A, okay.
And then like the force of B on A, like the, both of them.
Can you
Like
clarify?
the weight one, like the normal force of B on A?
Yes, so there is a normal force of B on A. And?
Oh, and the friction force of B on
Yes.
A.
And there's also a friction force of B on A. And then what else am I missing? External force, yeah. Yes.
Would there be another another normal force when it's because you have at this point that if the thing's already done, no, normal force would compensate for both edges.
Yes, exactly. Yes, normal force, like friction, is an adjustable force. So yeah, I haven't drawn them to scale, but this normal force is balancing the sum of these two. Yes.
Why isn't the force of static friction also on the free body diagram?
Isn't the force of static friction? The force of static friction is on the free body.
But for B,
Yeah. Yeah.
Yeah.
Okay, I mean, feel free to ask, yeah,
But we're thinking the opposite directions, like,
why these two?
yeah.
Any guesses?
Sure.
If one is A on B, other is B on A?
Okay.
What is it?
Is it relative forces?
Is it?
Action reaction?
Action reaction, yes, Newton's third law, yeah, that's right. So these are Newton's third law pairs. So this is the static friction of A on B, this is static friction of B on A. So they have to have equal magnitude but opposite direction. Similarly, this is normal force of A on B, this is normal force of B on A. And so again, equal magnitude, opposite direction. There was a question in the back again?
I think
Okay, yes.
Would it be the same thing for friction or is it just static friction?
Oh, no, anything.
Okay.
Yeah, regardless. Yes, so kinetic friction, gravity, normal force, anything always occur in action-reaction pairs. So yeah, so like, remember, the only reason why we're not seeing the third law pair of MBG is because that's in the Earth's free body diagram, which we're not really concerned with, right? And so, but it's there. Other questions? Okay, and then we'll do one more, which is the overall free body diagram. And so in the overall free body diagram, we'll have normal force of the floor on AB. We'll have the combined force of gravity, and we'll have the external force. Right, and so it's basically the sum of these two diagrams, right? And so we see that, oh, normal force of A on B cancels with normal force of B on A, static friction of A on B cancels with static friction of B on A, and we're left with the normal force from the floor, the sum of the two weights, and the external force. Oh, yes.
When you draw a free body diagram and like you label the velocity and the acceleration, do you have to write like them like with the little arrow on top to like say that they're vectors, or like can you just
No, you
draw
don't.
the direction?
Yeah,
Okay.
just draw the direction, yeah. Other questions? Yes.
Can we talk a minute about the static friction direction?
Sure, yes. All right, so one of the ways we can think about this, I'll give you two ways of thinking about this. So one is yeah, okay. So one is if there was, first imagine there was no friction between A and B. So then you exert this force on A, and what happens? B will just stay where it is and A will slip out from under it. Yeah. And so now look at that from two different perspectives. Look at it first from the perspective of A, right? It appears that B is going backward. And so to stop that motion, A will exert a force on B pointing forward, which is this one, right? And then similarly from B's perspective, A is going forward, it wants to stop that motion, so force on A going back. Another way you can think about it is, you can imagine, so we said that friction is like temporary bonds being formed between the two surfaces. And so we can imagine those as like bonds as like little springs connecting molecules in the two surfaces. So now when I apply a force on the lower one, what's going to happen? It's going to try to move, and so that's going to like start to stretch the springs this way. But the springs, what do they try to do? They don't like being stretched, they try to pull back together. And so they will pull backward on block A, but forward on block B, right? In order to keep their length the same. And so, yeah, that also gives you the directions of the force of static friction. All right, so once we have the diagrams, what's our next step? Equations, Newton's second law, yep, that's right. So we can start with the overall diagram. And we're really just concerned with the x direction. So I'll say f net x equals max, and so then I have f external equals mass of A plus mass of B times A. Yep, that's my equation, equation 1. And let me do equation 2 for block B. So again, I have f net x equals max, and now it's force of static friction, A on B equals mass of B times A. And really, that's all I need. I didn't actually even need its diagram, right? Because if I look at this equation, this is what I'm trying to find, the static friction on B. To do that, I need the mass of B, which I can figure out, and the acceleration. And to get the acceleration, I can just get that from this equation. Right. So let me just plug in for that. So I get mb times f external over ma plus mb. MB is 0.5 kilograms, right? I've given the weight, which is mg, but I've also said that g is 10 meters per second squared. So it's 0.5. F external is 10.5. And the combined mass, the combined weight is 35 newtons, and then divided by 10, 3.5 kilograms is the combined mass. And so we get 1.5 newtons is force of static friction. Okay. Slightly. We wanted to catch up on writing that. Yes.
So the only way we could find if the question say asked, what is the coefficient of static friction then, is if it were to be like, this is the max.
Right.
It would start moving.
Yes, or another way they code it sometimes is they'll say, this block is on the verge of slipping from the other block. So yeah, implying that it's at the max.
Sure.
Okay. All right, if there aren't any other questions, I'm gonna put the screen down. Oh, yeah. Take a picture. picture. All right. All right, okay, on to circular motion. Another 10 seconds. Alright, so ready to vote. What do you think? Okay, brief discussion.
Yeah, I would like.
I'm 16, going to slowing down.
Yeah. The elliptical.
Pretty much on gas.
Yeah.
Lower.
Okay, okay. Let me copy that. Down.
So he
Always.
you have at a point where it's at.
Like to compensate for the acceleration. So it's
This
gonna
was
be-
really. So what you're saying was just, yeah, it speeds up and it starts to speed up again.
I honestly don't know.
I don't know the reasoning. It's sort of like. Yeah, they're not really intended.
All right,
they're not
get ready. And
Right.
be ready to defend your answers also. Show me your votes. And, all right, mostly for C, C is correct. David, you wanna give it a shot?
Me?
Yep.
Of course. So I think that like the straighter the angle towards the point S, the acceleration vector has, like the less the centripetal, like the less the centripetal acceleration takes up force and more like the direct acceleration.
Tangential acceleration, okay.
Yeah. So I don't know if I'm like really explaining it elegantly, but I guess like the ratio of like the force that's like swinging it around versus like taking it directly towards S is higher at P, and then it's like the exact opposite at R. So I just thought that it would kind of move like, you know, it'd speed up when it gets to P and slow down when it gets to R.
Okay, you've got the basic idea, as you said, elegance could improve a little bit, but you got the basic idea, good. So, but yeah, it's basically if we draw the acceleration vector when it's at point P pointing towards S, David's exactly right that you can split it into a centripetal component, which is perpendicular, and a tangential component. And we notice that the tangential component is in the same direction as the velocity, because we're told it's going around counterclockwise, right? And so if the tangential acceleration is in the same direction as the velocity, it's going to help it speed up. So it's going to speed up at P, right? Reach its maximum at Q, and then slow down as it comes over here, because over here you can see, oh, the velocity is this way, but the acceleration is like this. So there's an anti-parallel component to the acceleration. So it would slow it down over there. Questions? All right. Let's. Yeah, let's look at this. All right, so take a moment to read the question. Okay, any questions about the question, about the setup of the question? Okay, looks like some, oh, question about, yeah.
Is there an equation for velocity in a circle?
Equation for velocity around the circle. Well, I mean.
V squared over one of.
You can relate velocity to other things, yes, you can relate it to the centripetal acceleration. So looks like some of you are already starting on this. So in fact, let's go to discussion straight away. Go ahead and draw your free body diagrams in this at the top and discuss. So. Focusing is not.
Well,
Okay.
I think so I'm thinking it through is that basically
Wait,
is that
Right now, we're not considering.
The normal board. Yes, not at the top.
Okay. It goes to zero, yeah.
kinetic exertion wants to keep it like on.
Acceleration equal
And
to.
I think that force that provides
Yes, but I mean, yeah, it's just. Centripetal acceleration is top.
Oh wait. Oh yeah, now it's gonna be
Oh, right.
I just this, but it's not just the scale, that's because
So if you say,
at its top, it says the normal acceleration. Of course, I
squared
know
over
call
G.
it, so
Yeah. Squared over R.
Oh.
yeah, I remember.
Okay, yeah, that's.
So gravity acts on it, just call the acceleration.
Oh, that's cool.
So then what's the gravity? Acceleration.
This is the velocity.
So
Yeah, yeah, right.
Right.
And so what kind of acceleration is that? Centripetal. So you can find the acceleration.
It is just got it up there and it's.
Do you?
Yeah.
So
we can lemonade.
Okay. I'll give you another 10 seconds and then we'll vote. All right, get ready and show me what you think. Okay. All right. Mostly for E is correct. Eric, you want to?
Well, so my process is that I first shoot a free body diagram and determine that at the top, there's no normal force acting on it, so the only force acting on it is Fg.
Yep.
And then I use which is centrifugal force, and then, so I use the equation, AC equals to V squared over R. And then you use that to derive, you move R to the other side.
Right. Okay, yes. But yeah, that's exactly right. So first thing is we draw the free body diagram, and as Eric said, there's only one force acting on it, which is the force of gravity. And so that's causing an acceleration downward. And we know the velocity is like that. So this is centripetal acceleration. It's perpendicular to the velocity. And so, so then if I choose this as my positive y direction, then I can write f net y equals MAY, and so that becomes MG equals MAC, which is equal to M V squared over R. And so then I can cancel the M's and I get G is equal to V squared over R. And I can solve for V. Yep. So that gives V is equal to square root of R. Question, yes.
Sorry, like it's a little hard.
Oh, yeah, sure.
No, but so the MAC, like where does the
Yeah.
M, I'm not sure where the M comes from, because isn't it just the acceleration is V squared over R?
Yes, that's why I plugged, so the next line I plugged in M times V squared over R.
Okay, I guess, maybe I'll ask my question in a different way, like I did V squared over R equals MG, so like what was wrong about doing that?
Well, V squared over R is the formula for the centripetal acceleration, not the centripetal force.
Oh, okay, so then you have to add in. Oh, okay,
Mass
so
to
just
get-
because you wrote like the AC, so I thought, that, yeah, that's what we were using.
No, but yeah, it was M times AC, yeah, exactly.
Yeah, I wrote those.
Other questions? Okay, and oh, there was another way that you could have gotten the answer if it was multiple choice like this. It's the only one with the right units. If you check all the other formulas, they won't give you the right units for velocity. Right, like you could see over here, you'd have meters per second squared over meters, so you just get over second squared, square root is just 1/seconds. So yeah, none of the others will give you the right units. Yeah. All right, let's actually do a demo showing something similar. Let's come around the demo. There you go, thanks. All right, so this is not quite the same because it's a ball rolling down the track, but it's pretty similar. So first I'll show you when it doesn't quite make the loop. Okay, and so if I release from here, actually, first the sort of naive thing you might think first is that, oh, if I release it from like the same height as the top of the loop, then it has enough energy to get there. But it doesn't have, what will happen, you will see, is it doesn't have enough speed to complete a circle of that radius. Right, it just fall. If I do it from this height, it will get further, but it will still not quite make it. Right? And if I start from here, now it has enough speed. But what I want you to also do is just listen to the sound of it as it goes around. Right, and you would have heard that like slight pause in the rattling, right, as it went near the top, and that was because it wasn't quite touching at the top. The normal force went to 0 at the top. So then, yeah. Questions? Yes.
If there were no friction when you released it at the top that was directly aligned, or at the space that was directly aligned with the top of the circle, would it have reached the top of the circle?
No, still no. Yeah. Basically, let's see, how do I put it? Simple way to see it is, if I released it from no friction, I released it from the same height, that would mean that when it got to the top, it would have 0 velocity.
Yeah.
Right, which is not enough acceleration for it to do a circle. Because the acceleration would be V squared over R. So yeah, I wouldn't be able to make it. Yes.
Is there a difference in the result if you had friction and if you don't have friction?
Yes. Well, there are two things. One is, in this case specifically, it is actually rolling instead of sliding, right? And so it turns out, we'll see this later in the course, to have something roll, you actually need friction for it to roll, right? Because your tires need to grip, right, in order to roll, otherwise it will just slide. So first of all, if you turned off friction, it wouldn't roll, it would just slide, right?
Yes.
And then, but even if it was just sliding and not rolling, then yes, friction does play a role. It does basically lose some of its energy to heat because of friction. And so, yeah, you would need to start it from a little bit higher in order to have the right velocity in each of them.
Without friction.
With friction, you need to start it from a bit higher. Yeah. Oh, yeah.
Is velocity the same at every point in the circle?
No. Yeah, no, that's a good question. Yeah. It's definitely like slowing down as it goes up the circle.
But at different points in the circle, there are different forces, so the formula will be different.
At different points in the circle, there would still be some normal force over here, right? It would be a combination of normal force and gravity. And so there would be a combination of centripetal and tangential acceleration. And so it'll be slowing down as it comes up. But then right at this point, there's only gravity, and that's perpendicular to the velocity. And so it's only centripetal. Other questions? All right. Let me show you. Example. Here. I'll help you out. All right. So. Yeah, we'll do this as our last circular motion example. Well, maybe not the last. Actually, wait, hold on 1 second. Give me a second. Let me see if that's the best. No, okay. We usually talk about bank curves. Right. So. Okay. Well, first talk about this very briefly, and then talk about bank curves. Get ready. What do you think? Okay, mostly for D, D is correct, yes. So the idea here is that, yeah, I'll draw that. The idea is that if you have a car going in a circle, right? This is the top view, the overhead view. So the car is taking a turn. Your natural tendency in the car is, by Newton's first law, is to just go in a straight line, right? The car is basically turning underneath you, right? And so you're trying to continue in a straight line, and the car is moving to the left. And so it feels like you're moving outward, but really all that's happening is that you're continuing in a straight line until the door presses on you, and then you feel the force of the door. All right, so one thing that we do to help cars with turns is use a banked curve, right? And so if you've driven or just even been driven and taken an exit ramp, so you know that as they do that curve, the road is sloping. Yeah. Yes. So we can imagine that. You can imagine the car is heading into the screen.
And turning left.
And turning left, yep, which you can figure out from the normal force, yep. And it is moving at a speed below the design speed for the curve, but it's not sliding on the road. Seconds, and then I'll ask you to close. All right, get ready. Show me what you think. The variety of answers. Okay, maybe I guess we'll pick up on this next time since it's yeah. Right, so yeah, so next time we'll finish discussing this question and we'll move on to work. Oh, and our photo now.
Are you gonna post the extension?
Because
Are you gonna post the Are you gonna post the answers to the practice? Regardless of whether. And I know.
Yes.
Yeah, please bring a calculator to the exam.
From like
Literally.
off the.
I used to hold them.
I saw them, I'll take a look at.
And I get that because they just like things. Especially that.
I played Macy. R, T, and. So, but I think the solution that if used in H2 to represent the output.
We did one. Oh, well, that, yes, no, I think we changed the question at some point. Yeah, we changed the question. We thought it looked a bit nicer in,
Yeah.
but that's all, yeah.
Do you wanna?
Yes.
I wonder if it's staying them.
Oh, I see,
Yeah, I'm
Yeah.
Tendency.
The tendency to stay straight is by.
So what if?
Well, the friction wouldn't push you against the door, because, from the car seat's perspective, you are moving outward. And so friction would try to hold you in. Yes. Oh, I'm sorry, I should have clarified. This was not like a vertical, like this was not, this was an overhead wheel. So gravity would have, yeah.
Would have been done.
Thank you.
So like it increases here because the tangential velocity is gonna be this way.
Correct, yes, in the same direction as the velocity. The tangential acceleration is towards S, right? So when you draw, like, we know it's going counterclockwise, so the velocity is this way, but the acceleration is this way. Right, because S is over here. And so when you split your acceleration up, you get that, oh, A tangential is the opposite direction to the velocity. Yeah. So this one.
And in this case, so the tangential.
So yeah, here at point P, the velocity and the overall acceleration are roughly in the same direction.
Oh, so the acceleration is going to report you towards S.
Yes, that's what the problem
Oh,
said, yes, yeah, yeah,
Thank you.
sorry.
Calculator, I know any I can borrow.
Yes,
No,
yes.
that's okay.
Well, I mean, there's, at the exam, I'll bring a few calculators, but I don't want people to like rely on that,
Yeah.
but yeah, yeah.
Hello, Rosie, how you doing?
Hey,
Um,
how are you feeling now?
feeling better, thank you. Yeah, thank you for all your emails and your support. I don't know if you got my email that I sent you.
I
this
saw
morning.
that when it arrived, I haven't read it.
Right, so I wasn't able to finish the homework. So I was wondering if you could potentially email it just about time.
Okay, yeah, this is just the corrections or the first submission?
That's the first submission.
First submission, okay, email it to me.
I'll email it to you. Just trying to finish as soon as possible.
Let's see. Let's see, today's Monday, by Tuesday night?
Yes, that's fine. Okay. Thank you so much, President. Have a good one.
You too.
Can I look at the last?
Oh, the last one.
Oh, yeah, yeah, yeah. I mean. I don't know.
It does help if you draw a picture, so.
I mean, I think friction is going this way, just cause like, from a like, I've seen the scenario where you send something on like a main curve, and it's going fast enough that it will rise.
Right, it's going fast enough to rise, but here we're saying it's going at a speed
So
below,
the
yes.
friction is here, but it's, I think, right? Like,
Well, which case are we considering, when it's going too fast or when it's going too slow?
if it's going. Oh, it's not sliding on the road. It's below the, okay.
Right, so not sliding simply tells you that it's static friction,
Yeah.
right, not kinetic,
Yeah.
and it's below the design speed. So which way
Actually,
is the
So
friction?
that means friction's pointing out,
Up, yeah,
I
but acceleration is here,
to the center of the circle, it's so horizontal.
okay. Okay. Yeah, that's. I guess of the bank curve is not.
Right.
Don't look at me, it's not going
I
in
didn't read
circles.
question, right? Yeah, I
Right,
can
not
see
to
the
the
last
center,
question.
but yeah, that's-
Okay, cool.
Thank you.
Thank you.
Did I get a sticker? Oh, thank you.